Welcome to this presentation on an algorithm for bichromatic sorting with Polylog competitive ratio. This is work by Mayank Goswami and Riko, and I'm Riko, and I'm going to give this presentation. This presentation can also be found at the URL that is in the first line of the slides, if you want to go back to that. The problem we are addressing is in the framework of sorting with priced information. This is a generalization of classical unit cost sorting, where the input consists of a graph, of an undirected graph, where each edge has some cost attached to it. And the cost is the cost to compare the endpoints, the vertices Vi and Vj. If the edge is not present, then the two points cannot be queried, which we can also think of as infinite constant. Classical sorting is the special case where G is the complete graph and all the costs are 1. The algorithm can make progress by performing comparisons, by querying an edge, with the outcome that one endpoint is shown to be smaller than the other in whatever way the underlying truth is. And this means that the input, without this being visible to the algorithm, consists of an underlying directed DAG that represents the outcome of all the comparisons. And for this framework to be meaningful, there must be a directed Hamiltonian path within G prime, and we call this within this directed version of G, and we call this H directed. And so the task of the algorithm is to sort, to discover this directed Hamiltonian path, and which means that we want to find a sequence of vertices such that the outcome of the neighboring comparisons is as described by the path. And the cost of the algorithm is just the cost of the edges it queried, and the cost of the Hamiltonian is the cost of all these edges that are on the Hamiltonian. This cost of the Hamiltonian can be understood as the cheapest proof of the output being correct, which we typically also call a certificate of the output. And now the performance measure that we're working with is the competitive ratio, as it's called, where we divide the cost of the algorithm by the optimal cost of the Hamiltonian path. And like everywhere else, we are interested in finding an algorithm with a small competitive ratio. Maybe on a side note, this competitive ratio is not to be confused with the competitive ratio of an online algorithm. In our setting, there is not really an online aspect of this graph being revealed, or the online aspect is something that is very much guided by the algorithm querying edges. The underlying truth is there from the beginning. This set of problems, this family of problems, has been proposed in a Stock 2000 paper by Sharika, Fagin, Goswami, Kleinberg, Ragavan, and Sahai. And they go about and work with many other things with priced information, and they have this nice quote here where they mention a special case where sorting items when each comparison has a distinct cost appears to be highly non-trivial. Suppose, for example, we construct an instance of this problem by partitioning the items into sets A and B, giving each A to B comparison a very low cost, giving each A to A and B to B comparison a very high cost. We then obtain a very simple non-uniform cost structure in the spirit of the well-known hard problem of sorting nuts and bolts. And this alluded to sorting with priced information with two sets we call for bichromatic sorting, and this is the problem all of our work, all of this in the presentation here today is devoted to. So To be precise, bichromatic sorting has as an input graph a bipartite graph with the two parts being A and B, and two values, alpha and beta, where we have the normalization assumption that the red-blue, the bichromatic comparisons have cost 1, all red-red comparisons have cost alpha, and all blue-blue comparisons have cost beta. And as was already alluded to, and when it's easy to convince yourself, that the only interesting case is if both alpha and beta are above 1, are more expensive than the monochromatic, that the monochromatic comparisons are more expensive than the bichromatic ones, and without loss of generality we can also assume that alpha is smaller than beta. But we're not going to use this assumption very much. And now, kind of as the first guideline where we stand is that the cheapest proof, this cost that we are comparing ourselves to, can vary quite a lot between all edges on the Hamiltonian path being bichromatic edges, which we call the perfectly interleaved instance, where we have n red elements interleaved with n blue elements. But then if all the red elements are smaller than all the blue elements, or vice versa, then we end up with a cost that is very much dominated by the monochromatic cost, and so we have this range of costs between 2n minus 1 and alpha times n minus 1 plus 1 plus beta times n minus 1. So there is quite a range. If alpha and beta are big numbers, then there's quite a range of costs that we might relate to, and we'll have to find an algorithm that is good no matter what the underlying instance looks like. And what we are going to present in this talk, what our main technical insight, is that we propose this algorithm we call inversion sort, and we show that it achieves with high probability a log to the third of n competitive ratio. So let's get right to it. To explain inversion sort, let me start by focusing on a simplified setting where alpha and beta are extraordinarily high. So think of it as alpha and beta being at least n squared, such that doing all the bichromatic comparisons is costing less than doing a single monochromatic comparison, which is somehow basically putting us into a setting where the graph is bipartite, where all the monochromatic edges have infinite cost, and then what is left is that we want to extract as much information from this graph as we possibly can without using monochromatic edges. And that means that we want to identify these stripes of monochromatic stretches on the Hamiltonian. And again, for the sake of simplicity, we can see that there is this perfectly interleaved case, and which is much resembling the nuts and bolts setting. And then the other extreme would be a setting where all blues are smaller than all reds, and we actually, in a second phase, need all bichromatic comparisons. So for the next part of the talk, assume that alpha and beta are really big, and that we run this classification of the situation by bichromatic comparisons and leave the final sorting to a second phase where we then do the required monochromatic comparisons, which then also is kind of obvious because this needs to be done and there is no additional unseen difficulty in it. So here are the technical ideas, the ingredients into this inversion sort, where we have you can think of it as a BFS style generalization of quicksort. And so that means that the pivot, the single active pivot, is replaced by what we call a backbone, which is a sequence of alternatingly red and blue elements that are compared between each other. So they already form a sorted sequence. And then everything else is sorted into this backbone, which means that if it's a red element, it's compared to all the blue elements on the backbone, leaving a single bucket between blues that can be identified by the red element on the black backbone. And so this is one state of our algorithm, and we can advance the state if we find a pair of inverted elements. A red and a blue element that can be placed between a red and a blue that are already on the backbone. And if we find this, then we extend the backbone and we extend the classification of everything that is not in the backbone by doing the required comparisons. So let's start with the little video of this, where we see that initially we have the backbone just consisting of an artificial smallest and biggest element, and then everything else is in the corresponding buckets. And now randomly we choose elements to try to find inversion on, and now we already found the inversion and we classified everything else with these two elements. And now we continue classifying elements back to a classical situation, and now we find elements that we try to find inversions with, and then we classify according to these new backbone elements. And if we do this long enough, then eventually in this setting, in this particular example is a perfectly interleaved example, so eventually we will see a sorted sequence of alternating red and blue elements. And now here, once we are in this where the bucket sizes are 1 deterministically, we end the algorithm. So this was the case where it's perfectly interleaved. Let's look at another little animation of what this algorithm does, where it's not perfectly interleaved, and again we start out the same. The algorithm is the very same. It doesn't know whether it's perfectly interleaved or not. Well, here just the cardinalities reveal that it's not perfectly interleaved, but nothing else is known to the algorithm. So it proceeds by extending the backbone and re-establishing the invariants, and now it tries to find new inversions. This is what we see here, that it selects elements and tries to find inversions. And if I remember correctly, then this will not lead to further inversions because we already see the truth revealed with the comparisons done already. So if we go back to a more systematic description of inversion sort, what we do is that we select one random element in each bucket, so that's both red and blue elements, and then we do the comparisons of the neighboring selected elements in the hope to find an inversion. And now, if we don't find an inversion, it's a random experiment, it could be that there is nothing to be found and we don't do anything, and otherwise we more or less in parallel, conceptually in parallel, put all these pairs onto the backbone and reclassify the non-backbone elements. And the final step is when we stop this thing, and this is when we realize that we did sufficiently many bichromatic comparisons on a pair of buckets such that we could as well have done all pairwise comparisons between two buckets. And then we stop the random process and just do all these comparisons, and that finalizes the situation locally. And then we do this and take this part of the graph, or part of the backbone, out of the runnings of inversion sort. And then, now that we are in general, alpha and beta are not close to infinity, so we actually should use the monochromatic comparisons as part of what we are as to speed up the inversion finding, and that's following a relatively simple idea. We just sample at the rate alpha or 1 over alpha red elements per bucket, and with the rate of beta or blue elements per bucket. So since we have these rounds of bichromatic comparisons for inversion finding, what we do is that every alpha rounds we insert a round of increasing the sample size. So in each red bucket we sample one not sampled red element, and then we put it into the sample by updating the minimum and the maximum. And to always have a sample, we assume that the element on the backbone that identifies the bucket is always part of the sample. And that means that we have augmented the situation by a sample that is growing bigger and bigger, and we include this minimum and the maximum in the inversion finding. So every randomly chosen element is compared to the corresponding min and max on the neighboring buckets. And of course, when we sample new elements, new minima and maxima, we compare them as well, because they also might be inversions. And if we find an inversion like that, then we run inversion sort creation of inversions, putting them on the backbone as always. So that leaves us with the analysis. The claim on the slide one more time is that this has a competitive ratio of log cubed. And I will not go through the details of this claim. This is where the paper has all the details that are required. Let me just point out the main ideas. So the first idea, and this is very much similar to what we see with quicksort, we realize that this random way of inversion searching leads to a refinement tree of logarithmic depths. So if we think of the backbone and how it develops, then we kind of do this in a analysis where we start from the ground truth, from the underlying graph. Then we see that this is splitting up the underlying Hamiltonian in a refinement fashion, and this leads to a refinement tree, and the depth of this tree is logarithmic, which means that we have a chance of remaining polylogarithmic. And then we realize that each level of this refinement tree, even though inversion sort is not working simultaneously on it, consists of disjoint subproblems of the underlying truth. And the other thing we realize is that this way of finding inversions, in particular augmented with the sampling, is a comparison cost that no algorithm can avoid. It's kind of an inherent difficulty in making progress to get anywhere, to distinguish locally the situation from the all red smaller than all blue. And so here we do something that is optimal. And the last thing that is making life a little more complicated is that because we have these buckets and the algorithm does not know which elements are smaller and bigger than the element defining the bucket, we have a phenomenon that we call spill-in, namely that these inversion searches are hindered, are slowed down by elements that are on the wrong side of this chosen pivot on the backbone. But there we can say that every log to the second, every log squared element is an active subproblem that is not disturbed by this. So with this polylog for bichromatic searching, what is it that we otherwise have? If we increase the number of colors, but the bichromatic comparisons remain at cost 1, basically inversion sort continues to work. The other observation is what we already used as a subroutine. The case where alpha and beta are infinity can lead to a solution to the bipartite setting, where then the notion of quality needs to be changed to an instance optimality framework. And that's something that is investigated in a different work. And then, of course, there is this thing that priced information in its full generality is, for many of the cases, wide open, and in particular, for most of these cases, for most of the cases that are not covered by what we did here, it is completely unclear whether a Polylog competitive ratio can be achieved. Thank you for your attention.